Hello, everyone. It is time to start. It's 1 o'clock here on Thursday. Thanks to everybody who has joined in. My name is Sturgeon, and I'm the outreach coordinator at the Indiana Geological and Water Survey. And today I'm going to talk about earthquakes that happen here in Indiana, both the science of them and how to prepare for them. I'm going to be doing mostly a screen share where I show a couple of different slides with diagrams and maps to illustrate what I'm talking about, but I may occasionally switch back and forth between the live camera view and the screen share. At the end of this presentation, I will save this program and post it to our Facebook page. So if at any point you need to leave or you just want to watch later on, that's going to be posted later this afternoon. All right, if you have any questions throughout the program, feel free to put those into the chat, either visible to everyone or directly sent to me, and I will be sure to answer them at some point during the program. Or if you think of questions later on, you can put those as comments on our Facebook page, and I will be sure to answer them. All right, we're going to go ahead and get started. So I'm going to share my screen. Here we go. Okay. So again, as I said, my name is Sturgeon, and I'm the outreach coordinator. So part of my job is educating Hoosiers about the geology of the state, and a good portion of that deals with earthquakes and our seismic hazards. So I'm going to be explaining the characteristics of earthquakes, just a general primer about what they are and how they're caused. One of the largest earthquakes that people know about in the central United States is the 1811 and 1812 New Madrid earthquakes, the series of earthquakes that happened a little over 200 years ago. So I'm going to discuss that and how it relates to the seismic hazards overall within this part of the country. Then we'll zoom in a little bit closer and we'll look at Indiana earthquakes. We'll talk about the different hazards that exist here because of our earthquakes. I'll review some of the recent earthquakes that have happened within our state, and then we'll talk about how to prepare for them at the very end. Okay, beginning with the basics. So an earthquake is a sudden release of energy that happens when two fault surfaces slip past one another. A fault is a crack within the crust of the earth that has movement along either side of it. So you can see on this diagram, one side is going up, one side is going down, and that plane between these two blocks is the fault. Where those two blocks move is the hypocenter underneath the ground, but then more commonly we call it the epicenter. That's just the point above the hypocenter directly on top of the surface of the ground where we actually feel the shaking and the shaking originates. So if this were an actual earthquake, the movement would be happening below the ground. The epicenter is where it is directly corresponding above, and then those earthquake waves would radiate out from one another. There are 3 earthquake waves that are generated when the fault has movement along it. There is a P wave, an S wave, and a surface waves. I'm going to go to the next screen and show you examples of each of those. So P waves are generated first. P stands for primary. This is usually either not felt or it's just a very small seismic shaking. The S waves are going to be the stronger shaking that you feel, and then the combination of those, what persists throughout the earthquake, however long it takes, is going to be called the surface waves, and that's where you get that rolling motion. So it's the combination of these things that produces shaking that occurs during an earthquake. One of my favorite examples of seeing these different waves, if we go back to 2017, there was a magnitude 8 earthquake in Mexico. And this is a diagram produced by IRIS, and they monitor seismic activity throughout the United States and broader around the world. So if I'm going to click this, and we can see, it's going to come up over here. Here we go. We can see the illustration of what happens when the earthquake began at the epicenter in Mexico. So you can see the initial waves were felt, and then a larger wave. It's being recorded down here, and I'll go back and play this again, and then more rolling surface waves, the combination of those. Coming from the south because it originated in Mexico. Here, I'll go back to the beginning. Here's those primary waves, small shaking. The S wave is much larger shaking. You can see all the seismometers are going crazy. And then the rolling nature of the surface waves, okay? Keep in mind that seismographs will pick up shaking that people won't necessarily feel. So I don't believe that there were too many accounts of people besides the southern portion of the United States that actually recorded feeling shaking from this earthquake, but the seismometers picked up that seismic energy as it traveled away from the epicenter. And the red and blue indicated up and down motion, okay? There's two ways that we describe and measure that motion that comes away from the epicenter or the hypocenter of an earthquake. These terms are called magnitude and intensity. They're measuring different things. Magnitude measures the amount of energy that's released at that epicenter, at the source of the earthquake. It relies on seismograph measurements, so those little squiggly lines that we saw in the previous diagram or that you've seen on the news when talking about any earthquake. Magnitude is measured using the Richter scale, which goes up to from 0 to 10. And usually, in most cases, magnitude begins to be felt around a 3.0. Below that, except in very specific places, people don't actually feel earthquakes in the magnitude 2, 2.5 or lower range. We refer to those as microquakes, and they're measured all the time on seismographs, but we don't actually feel it as shaking. Intensity is a different measurement, maybe not as common, but I think it's actually more descriptive. It measures the strength of shaking that's produced at a certain location, not necessarily the epicenter. It's produced at, intensity is measured at every different location that feels the shaking from an earthquake. It's determined by the effects of what shaking people feel and the effect that it has on buildings and structures. It's measured using the MMI scale, which stands for Modified Mercalli Intensity, and it's measured on a scale from 1 to 12. Okay, we'll begin with magnitude because that's a more commonly known scale of measurement for earthquakes. So again, earthquakes are measured up to a scale of 10. There has actually never been a 10 on Earth before that we know of. The largest known earthquake was a 9.5 in Chile in 1960. Once you get into the 9s, it's pretty much complete destruction, as you can see here. The earthquake several years back in Japan, for example, that was a magnitude 9.0. You can see the amount of energy that's released. It's on a logarithmic scale, so it goes up incredibly as you go from one magnitude to the next. So the same energy that's released in an average tornado would be somewhere around a 4 to 4.5. Okay, the energy that was released in the Hiroshima atomic bomb would be a little bit over a magnitude 6. Mount St. Helens closer to a magnitude 8. Okay, so you can imagine the intense destruction that would be caused by magnitude 9 or higher. And of course, the larger the magnitude is, the less common it happens per year. This is the Modified Mercalli Intensity Scale, or MMI. Okay, a little bit more complex looking, but I think it's a much more reflective and accurate description because, again, magnitude only describes the energy released at the epicenter, and unless you live right by the epicenter, you're not really getting a description of what the earthquake feels like in your local area. MMI does that. So it goes up to, I said it goes up to 12, so 10 plus gets into the extreme category. These words here are what scientists use to describe an earthquake. So when an earthquake happens in Indiana, for example, the Indiana Geological and Water Survey will put out press release and social media updates about the earthquake. And these are the terms that I will use when I write those updates. So a moderate earthquake, for example, is going to have an MMI of 5. Okay. Whereas a strong earthquake, I wouldn't use that term unless you start to feel an MMI of 6 or higher. MMI, intensity and magnitude, don't correlate exactly. Anywhere from a 1 to a 3 magnitude is going to be a 1 on the intensity scale, whereas a 5 to a 5.9 magnitude is going to be a 6 to a 7, for example. Okay, so but this has to do with the amount of shaking that you feel and the damage that occurs. And we'll see some examples of that when I get to specific examples of earthquakes. Okay, if we look worldwide at all of the earthquakes that occur globally, you can see the red dots there are indicative of earthquake regions. You can see that most of them occur along the boundaries of tectonic plates. This is something that we all likely learned in grade school. We learned about the Ring of Fire, these areas where tectonic plates are colliding or interacting with one another, and it produces earthquakes and volcanoes. Okay, 95% of all earthquakes worldwide occur at plate boundaries, and that makes sense. So the big question that I get very often is, why does Indiana have earthquakes? We are smack in the middle of the North American plate. We are very far away from any plate boundaries, so why do we get earthquakes? It's pretty interesting. So earthquakes within Indiana and then the larger central United States are the result of movements of faults that are buried very, very deeply below the ground surface, thousands of feet below where we're standing today. These faults were formed by a weakened zone that follows roughly where the Mississippi River runs today, and it occurred within the center of the North American plate. There were intense forces that tried to pull it apart and cracked the crust, basically. Those cracks have been very deeply buried, and those cracks are now our faults, which when they move, will produce our earthquakes. That event, that cracking of the crust, is known as the Real-Foot Rift. It began about 600 million years ago. Like I said, it occurs in the Mississippi River Valley, and it's an area where the crust tried to separate or rift, pull itself apart, and it didn't work. That's why we don't have an ocean in the middle of North America. So that failed rift weakened the crust in the center of the continent, and the 600, 500 million years of sediment and rock that have buried it means that occasionally those faults will move and they generate earthquakes that we feel, even though we don't see faults here at the surface very often. This type of earthquake is called an intraplate earthquake, and it's very rare. It accounts for about 5% of all earthquakes worldwide. Okay, because our faults are very deeply buried, it does make it difficult to make accurate observations. We have to do more monitoring of these faults and earthquakes, and using more remote sensing techniques, because we can't see them at the ground surface like you can in other areas like California. Okay. A good example of a rift area, just to emphasize this part, the East African Valley, there's an active rift zone occurring there, and if we fast forward several million years, there will eventually be a small ocean that forms there, unless that rift for some reason begins to fail. So that it's a tectonic process that has happened throughout geologic time and is continuing to happen today, but it just so happened that it failed within the Mississippi River Valley, and that's what caused our faults. Okay. That rifting, that failed rift, caused two seismic zones, which both affect Indiana. The Wabash Valley Seismic Zone is located in southern Indiana, as well as Illinois, and a little bit into Kentucky. In Indiana, it runs roughly between Vincennes and Evansville. And then what's probably more likely to be known, the New Madrid Seismic Zone, runs along the Mississippi River Valley, down near Memphis. Okay, but both of these seismic zones, if and when an earthquake occurs there, they will affect Indiana residents. Let's begin with the New Madrid earthquakes, because it's pretty famous. So the New Madrid seismic zone, its most famous seismic activity was in 1811 and 1812 with what is now called the New Madrid earthquake series. This event occurred over a 3-month period in the winter of 1811 and 1812. It began with a magnitude 7.5 earthquake in Arkansas. Then again in January, there was a magnitude 7.3 near the town of New Madrid, Missouri. which is what the earthquake series is named after. And then just a few days later, on February 17th or February 7th, there was a magnitude 7.5, also near New Madrid, Missouri. In that same time period, so those are the three big earthquakes, but there were many smaller aftershocks that occurred as well. There were 4 earthquakes between a magnitude 6 and 7, which is still very strong shaking. There were over 200 magnitude 4 to 6 earthquakes, and then nearly 2,000 magnitude 3 to 4 earthquakes. So people really thought it was the end of the world. If we look at historical accounts in newspapers and journals, and I don't blame them, because that is a lot of shaking in a very short period of time. The culmination of all of these earthquakes, it severely changed the landscape down near the Memphis area. There were landslides, ground ruptures that formed in the surface, riverbanks filled, islands completely disappeared. There was an account, and a lot of times you'll hear about it, that the Mississippi River ran backwards. That's not entirely true. The large waves caused the Mississippi River to look like it was running backwards. The waves splashed back, flowing upstream. So it looked like for a small time that the Mississippi River was running backwards. And then there were sand blows, which is a formation of liquefaction where sand and water actually shoot up out of the air. The shaking, as you can see here, the epicenter down near Memphis. These numbers are using the modified Mercalli intensity scale. So the most intense shaking was down near Memphis. And as we go away from the epicenter, it of course gets less intense shaking, but it was felt as far as Boston, Massachusetts. There are historical accounts of church bells ringing because of the shaking in Boston. Okay. The New Madrid seismic zone is the most naturally seismically active area. That's what the asterisk means there. In Oklahoma, they also have very seismic active zones due to man-made activities, but the New Madrid seismic zone is the most seismically active area east of the Rocky Mountains. And when we compare it to paleo earthquakes, ancient earthquakes, we know that the New Madrid scale of earthquakes have actually happened before. In the year 1450, there was a magnitude earthquake that was similar in magnitude and location to the New Madrid earthquakes, and again in 900 AD. And so the big question is, when will this happen again? If we look at this hazard likelihood map completed by the U.S. Geological Survey, we can see that there's a 7 to 10% chance of a Mag 7 or higher in the next 50 years, and then up to a 45% chance of a magnitude 6 or higher earthquake in the next 50 years. That's a lot of variability, and it makes it difficult to plan. But there have been accounts to predict how much damage there's going to be so that we can begin to prepare for them. And the 2017 estimate looked at, if we were to have a magnitude 7 earthquake again in the New Madrid area, it would affect up to 12 million people and over $200 billion in damage. We're going to zoom in a little bit more and look at specifically Indiana earthquakes. There have been 44 earthquakes within Indiana's borders since 1817, since the New Madrid earthquakes. So that is roughly one earthquake every 4.5 years. They have been, of course, concentrated down in the southwestern part of the state where the Wabash Valley seismic zone is located, again, between Vincennes and Evansville. All of these little dots here are epicenters of earthquakes that have occurred since 1817. And then the red lines are faults. Okay, all of Indiana's faults are below the surface with the exception of 2. The Mount Carmel fault here between Bloomington and all the way down to Washington County, that is exposed to the surface, as well as the Kentland disturbance up in Newton County. Those are both exposed to the surface. The rest are all buried and we know about from remote sensing techniques. Within roughly the past 200 years, all of these earthquakes have measured between a magnitude 3 and a 4.9. So those are all within the moderate to weak intensity scale. Most recently, there was a magnitude 2.3 in Gibson County in 2015, and then a magnitude 3.1 very early in the morning in Knox County in 2012. If you can recall earthquakes that happened in other times, but other than May of 2012 and 2015, that would be likely because they originated in other states. Of course, seismic activity doesn't stop at the state border, but this map just shows what happened in Indiana. So if the earthquake happened in Illinois or Kentucky, of course we're still going to feel it if it's a strong enough earthquake, but this map is just showing what happened in Indiana. Oh, there's the New Hampshire Wabash Valley seismic zone. Okay. If we look at further back, further than 200 years, which is roughly the historical record of earthquakes and the introduction of seismographs, if we look at earthquakes that occurred much earlier than that, we use paleoseismic evidence. And we know that there have been at least 4 major earthquakes between the past 3,800 to 1,200 years. On this map on the left, every one of these black dots is an area where we have something called evidence of liquefaction. It's basically a sand blow where sand and water has shot up out of the air. It gets so pressurized by the seismic energy that it bursts up to get to an area of lower pressure. And we have researchers who've gone along all of these rivers and found areas of sand blows, and then they've used radiocarbon dating to date the sand blow feature and therefore the earthquake that produced that feature. Sand blows are only formed in magnitudes 5.5 and higher, so we know that these had to be moderate to large earthquakes that occurred. And if we take all of the ages that the radiocarving found, we can see that they happened around 4,000 years around Columbus, 4,000 to 8,000 roughly around Indy, 6,000 years ago over here in western Indiana, and then around 12,000 years ago there was another large earthquake in the southwest. Here's a little bit more description of those sand blow features. So that's caused by something called liquefaction, which is where soils temporarily lose their strength and they behave more like a viscous liquid rather than the solid that they are. It occurs in areas where you have loose sandy soil close to the water table, so where the groundwater is within 30 feet or so of the ground surface, and you have to have a magnitude 5.5 or stronger earthquake for it to occur. But you can see in this diagram there's seismic activity, earthquake waves traveling through the ground. That loose, wet, sandy soil gets very energized and it actually shoots up out of the ground. Here's a modern sand blow picture. We can also see areas where sand dikes, where the sand and water traveled through cracks below the ground surface as well. Okay. So that's one big hazard that occurs here in Indiana due to earthquakes is liquefaction. I'll go back to that screen actually. We have a lot of areas around Indiana that fit these parameters. If you live near a river bottom, for example, or a former river bottom, much like the town of Evansville, it's at risk for liquefaction if we were to have the right seismic conditions, if we were to have an earthquake of magnitude 5.5 or higher. So liquefaction is certainly going to be one of the biggest hazards for large earthquakes. Another hazard deals with the effects of seismic waves on specific geologic materials. If we look at this diagram on the bottom left, we can see the red line here is the seismic waves that are traveling away from the hypocenter under the ground. And seismic waves will actually intensify when they hit soft soil or alluvium rather than bedrock. And if we think about that, that kind of makes sense. Bedrock is more solidified. Its particles are not going to shake as much as loose, unconsolidated sediment that is actually going to shake more. So even if you live farther away from the earthquake, if your home or business is located on a floodplain, for example, loose, sandy, wet soil, the shaking is going to be stronger than maybe your neighbors whose house is on the bedrock, even though they're closer to the earthquake. An example of this is in the 1909 Terre Haute earthquake. It was a magnitude 4.7. So here on the map here, the red dot is the epicenter. located near Terre Haute. And on the colors here, the blues are lower amounts of intensity shaking, and the greens get into more intense shaking. And so right around the earthquake epicenter, it's the most intense shaking. And that makes sense. It's stronger waves closer to the center of the earthquake. As you move away from the earthquake towards Illinois, we start getting less and less shaking. But you can see it jumps back up in areas around Evansville and St. Louis, because those areas are located on floodplains. So you get more intense shaking because of the specific materials that those cities and areas are built on. Okay. The third hazard that we need to think of when we're looking at central United States earthquakes is a term called attenuation. Attenuation deals with the seismic waves and how they travel throughout a substance and the amount of energy that they contain. In the Midwest, our bedrock is relatively old, it's dense, it has already cooled down, and it is much older than the bedrock that forms out on the West Coast. If we compare two earthquakes of relatively similar magnitude, the San Francisco earthquake from 1906 and the New Madrid earthquake from 1811, both had similar magnitudes. Okay, you can see that the intensity of the shaking out in California, it doesn't really affect too many people. Too many people didn't feel it shaking once you get outside of California a little bit into Oregon. If we compare that to the New Madrid earthquake, you can see that there were people who reported feeling shaking of various intensities throughout most of the Midwest and Eastern Seaboard and down even into the southern United States. So the Midwest and East Coast rocks have that old dense bedrock, and seismic waves can travel really well through that without losing any energy. So you feel higher intensities over a greater area. This is a phenomenon known as low attenuation. Whereas out west, their bedrock is relatively young, it is still cooling down, and it is not as dense as the bedrock that we have in the Midwest and East Coast. So they have a high attenuation, which means that their rocks are not going to transmit those energies over large distances. So again, even if the earthquake doesn't happen in Indiana, we could still feel the effects of it because of our bedrock that exists in this part of the country. Okay, some recent earthquakes that have occurred. The most recent I mentioned earlier that occurred within Indiana was in 2017, but it was a very low magnitude. The ones that people could feel, 3.0 and higher, are listed on this page here. So in 2017, there were two relatively small earthquakes, but within the magnitudes that people could feel. In 2017 in Illinois, a magnitude 3.8 and a magnitude 3.1. In 2012, there was a 3.1 and a 3, both within Indiana. The Knox County was out near Vincennes. Back in 2011, this one received quite a lot of press attention. There was a magnitude 5.8 near Mineral, Virginia. It's near Richmond, Virginia, and that's the one that cracked the Washington Monument and produced some damage that they had to, enough damage that they had to repair the monument itself. There were people in Indiana who reported feeling shaking from that earthquake, which is an excellent example of that low attenuation where the seismic energy can travel very far distances before it loses any strength. One of the largest that's occurred within just modern memory, 2008, there was a 5.2 in Mount Carmel, Illinois, so just a little across the border from Vincennes, Indiana. And if we take a look at that one here, you can see that people reported feeling strong shaking right around the border. It gets less intense as you go away from the epicenter, except in some areas where maybe you're near river bottom. Okay, here's pictures from that 2008 Mount Carmel, Illinois earthquake. You can see that bricks fell off of unreinforced masonry buildings. There were chimneys that cracked, porches that fell off, gravestones were turned on their axis, caused quite a bit of damage. Okay. When we're looking at all of these, both modern earthquakes and paleo earthquakes, the big question is, can we predict when the next one is going to occur? And the answer is always no. And it's very unlikely that scientists will ever be able to predict earthquakes within the future. But because we know the hazards and the geology that exists here in the central United States and in Indiana, we know that we need to prepare for earthquakes. The central United States is number 3 for earthquake hazards in the US. Alaska and California are 1 and 2. Those ones make sense. They're on tectonic plate boundaries. They have a lot of earthquakes every year. The central United States, a lot of people don't think of for earthquakes, but when we go back to those 2 seismic zones, the New Madrid seismic zone and the Wabash Valley, that actually increases our seismic risk. And then because of our bedrock and the geologic materials that we have here, it increases our risk. So that's why we are number 3 in the country. So we need to know how to prepare for these events. The 3 big things that you can do to prepare for an earthquake, they're fairly simple. This little cartoon diagram on the left is something that we developed for children when we go around to schools to talk about earthquake preparedness, but it's something that everybody can do, and these actions are either free or relatively inexpensive. The first one does require a little bit of money. You do have to purchase materials to pack a disaster kit, but we recommend, and other preparedness organizations recommend, that you pack enough food, water, safety materials to sustain your family for up to 3 to 7 days without power. When large earthquakes occur, they can knock out power lines, they can knock out gas lines, they can knock out the electricity. So we need to be able to survive an event like that without overwhelming the emergency services that are going to be helping people who are injured or other more drastic situations. So packing things like bottled water, a first aid kit, non-perishable food, all of these things are going to be very useful. And of course, you can use these in other natural disaster events as well. Things like a winter ice storm, or power outages in the summer. So it's not just specific to earthquakes. The materials that I have in my home, I put into a 5-gallon bucket. I've also seen people use backpacks. I got about $25 worth of materials from a big box store. I put them in that 5-gallon bucket. It sits near the back door of my house, so it's ready when I need it. You don't want to be looking for these materials after the lights have gone out. The second thing that you can do to prepare for an earthquake is free. It just requires some mindfulness. It is to practice the earthquake drill, which is known as drop, cover, and hold on. If you went to school, grade school several decades ago, you might have heard or been taught to get into a door frame when an earthquake occurs. They've since found that you are more likely to get injured moving to that door frame than you are if you just stay where you are, get down on the ground, and get under something. The biggest hazard in the United States for injury is going to be things falling on you. So you don't want to run out of the building. You don't want those unreinforced bricks causing damage, of course. You want to stay where you are, get under something so that when books or ceiling tiles, what have you, are falling, it falls on the table or the chair and not your head. Okay, and this is something that every public school in Indiana now practices. There's actually a national earthquake drill coming up, I believe, in about a week or so, and they will all practice this where they get under their desk and practice, but it's something that as adults who are no longer getting those preparedness messages, that we also need to be practicing as well. The third thing just requires a conversation with the people that you live with. You want to choose an outdoor meeting location, a safety spot where you meet after a disaster. Again, this is something that you can use with other kinds of natural disasters or say fires that occur, but you want to go out of the home after the shaking stops. So you stay inside, just take cover as quick as possible when you feel shaking, but then when the earthquake is over, you go outside. You do this for 2 reasons. You want to make sure that everybody else comes out. You know that if somebody doesn't come out, that they might be trapped and you need to call for help. You also want to go outside so that you can inspect the structure for damage before you re-enter. So places like a mailbox or the big stop sign down the street, things like this, that you can practice with your children, for example, and just practice meeting there for once in a while so it's ingrained in them that that's where you go when something bad happens. This is also something that you should have in place for your workplace and other places where you go frequently so that you have that kind of muscle memory of where to go when something happens. There are other preparedness activities that you can do, but these three are the big three that really save lives in a very safe, easy way. Some other ways, of course, if you are using a wheelchair or a walker or a cane, you still want to practice drop, cover, and hold on, but the techniques are just slightly different. Other things that you can do, you can secure furniture and large appliances around your home. You can make sure you know how to turn off the electricity and the gas line in your home, all sorts of other techniques. But those three, the disaster kit, the earthquake drill, and choosing an outdoor meeting location, those are the three easiest ways to be prepared for the next earthquake. There are additional resources. I know I'm grazing over the preparedness techniques. I wanted to leave time for questions, but there's a lot more information about the science of earthquakes and how to prepare for them on our website, as well as an interactive map where you can see all of the earthquakes that have occurred within the central United States and the magnitudes that those earthquakes were, as well as you can look at the seismic stations and you can see live readings of seismic activity within the United States. All of those are available on our earthquake webpage, which is igws.indiana.edu/earthquakes. Okay, that is the end of this presentation. I'm going to open it up for questions to see if anybody has some. Okay. Does anyone have any questions? That was a very quick overview of our seismic hazards and then preparedness. But it's an important topic and one that I don't think gets as much attention as it deserves, seeing as we are number 3 for earthquake risk in the US. Okay, a couple of questions in the chat. How fast do earthquake waves travel? There's no single number that I can really give there. Earthquake waves are all individual in terms of the depth that they occur below the crust, how much movement there is along the fault plane. Some earthquakes just move a little, some move a lot. So it can vary. That's a good question, though. Okay, another question that just came in, is there a good place to see the Mount Carmel fault that is readily accessible? Yes, there is actually. Along, I believe it's State Road 4546 outside of Bloomington. There is a couple of outcrops if you're just traveling on that road. And if you see areas where the rock layers no longer match up, they are now shifted. That's the Mount Carmel fault. There's also an outcrop of it within the Hoosier National Forest. If you give me 1 second, I can grab something to show you where that exact location is. Here we go. So this book here, Indiana Rocks, it's got 50 places you can go see interesting geology. Let's see, one of the sites in here, site number 29, is the Mount Carmel fault, and it gives you latitude and longitude for one particular outcrop that's just on the side of that road. So Indiana Rocks, and it has the lat long for an accessible area where you don't have to hike to it or go on private property. Good question. Okay, I got a question about the types of faults that we have here in Indiana. So there are, if we just look at fault motions, we have 2 different kinds of crust. We have 3 different kinds. We have a normal fault, we have a reverse fault, also called a thrust fault, and then we have strike slip faulting. If we take 2 pieces of crust and they move side to side, that's strike slip. For example, I'm blanking on the name. the large earthquake out in California. Sorry, I can't think of the name of it. That is largely a strike slip fault. The San Andreas, thank you. The San Andreas fault, that is mostly strike slip. Thrust faults are areas where you have one plate that moves up relative to the lower plate, the hanging wall plate. We don't have those in Indiana. All of our faults go like this. It's called a normal fault. And so it's not going to be producing large sections that are moving up. All of our faults are going to produce a down motion. So when we looked at the New Madrid earthquake series, there was a lake that was actually formed during one of those large 7-point-something earthquakes. It's called Reelfoot Lake. It's in Tennessee, I believe. And that occurred because the faulting went down and waters then filled in that new depressed area. Okay, a couple other questions that have come in. Do geologists think that rebound from ice age glaciers could be responsible for movement in some of the faults? That's a really good question. So glaciers were these mile-thick sheets of ice that moved down and back and forth over Indiana within the past 2.6 million years, and they left Indiana roughly 10 to 12,000 years ago. Because of the immense weight of those ice sheets, they actually depressed the crust. And now that the ice has melted, the crust is starting to bounce back up again, kind of flex back up. It's called isostatic rebound. So there is some motion where the crust is starting to move back up, but that's at a much more superficial level than our earthquake fault and our faults. Our faults are thousands of feet below the ground surface, so there hasn't been any correlation between that isostatic rebound and our faults. But that's a really good question. Doesn't mean that activities can't trigger faults. I mentioned Oklahoma, that they have actually surpassed the Midwest in terms of seismic activity due to hydraulic fracturing, or fracking as it's commonly called. So that's where they're pumping pressurized solution down into the ground in order to break apart hydrocarbons, oil, gas, out of areas where we can't get them with more traditional drilling techniques. And that pressure change under the ground surface has triggered a lot of earthquakes down there. In Indiana, we've actually done studies. We've used hydraulic fracturing for over 100 years. It's been going on since the 1800s. But we have found that none of our earthquakes have been attributed to hydraulic fracturing. So isostatic rebound and hydraulic fracturing, neither of those are causing any of our seismic activities in Indiana. The sand blow, somebody asked about sand blow references. So sand blows, sand dikes, all of those are features of liquefaction, and they're the two scientists who did most of that work. Their last name is Munson, M-U-N-S-O-N. They were the ones who collected all of that data for sand blow locations throughout Indiana riverbanks, and then did radiocarbon dating. They're actually archaeologists. They used archaeological evidence as well to help narrow in the age of those events. And if you look up sand blows and New Madrid, there's also a lot of evidence of paleo earthquakes around the New Madrid area as well. There's information about that on the U.S. Geological Survey's website. Any other questions? These are good ones. Anything I didn't address that you have a burning desire to know about? Yes. Okay. If you think of any other questions, feel free you can send us an email. Our general email is igwsinfo@indiana.edu. I put my personal information on the PowerPoint slides there, or you can just shoot a message to our Facebook page. Any of those, I will be able to address and answer your questions. I really appreciate all of you putting aside some time in your day and your schedule to learn about Indiana earthquakes and our geology here. I appreciate you giving up your time for that. And if there's any questions I can answer in the future, please let me know. I'd be happy to help. I will be sure to save and post this presentation here in the next few minutes. Thank you, everybody. Have a good rest of your day.